Hydrogen, represented by the symbol H and atomic number 1, stands as the lightest and most prevalent element in the universe, making up about 3/4 of all ordinary matter. Under typical conditions, hydrogen exists as a gas of pairs of atoms called dihydrogen, with the formula H2. Nearly all stars, such as the Sun, are largely made of hydrogen in the plasma state, while on Earth, hydrogen appears in the form of H2 gas and as part of compounds including water and organic molecules. The most common form, protium or 1H, features just a proton and an electron. Artificial creation of hydrogen gas dates back to the 17th century through mixing metals and acids. During the late 1700s, Henry Cavendish recognized hydrogen as an individual substance, noting water is produced when hydrogen burns, giving rise to its name, meaning water former. Observing how hydrogen absorbs and emits light shaped the birth of quantum mechanics. Hydrogen mostly behaves as a nonmetal except under extremely high pressures and easily forms covalent bonds with many nonmetals. It takes part in acid-base exchanges by transferring protons between molecules. In ionic compounds, hydrogen appears as either a hydride anion, carrying a negative charge, or as a hydron cation, H+. Hydrons, though bound to water molecules in solution, play a defining role in the behavior of aqueous solutions, as shown by concepts like pH, while hydrides are rare due to their instability in water. After the universe cooled enough, neutral hydrogen atoms emerged roughly 370,000 years following the Big Bang. Later, with the appearance of stars, most hydrogen floating between galaxies was reionized. Today, nearly all hydrogen is obtained by converting natural gas through steam reforming, though it can also be acquired by splitting water with electricity, a pricier technique. It is mainly applied in processing fossil fuels and making ammonia for fertilizers. Hydrogen is now being explored as a fuel source in devices that generate electricity. The hydrogen atom's electron possesses a ground state energy equivalent to minus 13.6 electron volts. Transitions between energy levels create light of specific wavelengths, which establish the hydrogen spectral lines. Each energy level divides into finer hyperfine states because of interactions between the electron and proton spin. Accurate calculations of hydrogen's energy states are important in setting fundamental physical constants, with advanced quantum theories attributing corrections from relativistic, self-energy, and vacuum effects. Chemical nomenclature distinguishes among hydrogen's neutral form, the hydron, H+, and the hydride anion, H-. The name proton typically refers to the H+ cation of the dominant isotope. Hydrogen is unique for having 3 naturally occurring isotopes: protium, 1H, deuterium, 2H or D, and tritium, 3H or T. Protium, with only a proton, makes up more than 99.98% of hydrogen. Deuterium contains 1 neutron and is non-radioactive, showing up in heavy water, which finds use as a neutron moderator in reactors and as a tracer. Hydrogen's history features key figures. Boyle found it via metal and acid reactions. Cavendish identified it as an element, producing water when burned. Lavoisier confirmed its elemental status and role in water formation. During the 19th and 20th centuries, hydrogen filled balloons, powered experimental engines, and became central to quantum theory's development due to its simple structure and atom spectrum. Chemically, dihydrogen is generally unreactive due to the strength of its HH bond, but does participate in forming complexes with metals and in chain reactions with halogens. Hydrogen is woven into compounds as both a cation and anion, including a vast array of hydrocarbons and organic molecules, underpinning much of chemistry's structure, especially through acid-base interactions. Hydrogen bonds play a vital role in the behaviors and properties of molecules, key to the architecture of biological molecules and governing phenomena, like water's unusual characteristics and the folding of proteins. Proton transfer in solutions associated with acids shapes the pH scale, a numerical measure linked to the concentration of hydronium ions. Proton is often a label for hydrogen cations attached to other molecules in solution rather than for free protons. Hydrates, formed primarily between hydrogen and metals, can be ionic, covalent, or metallic, and often release hydrogen when exposed to water. In compounds with lightweight elements, hydrogen forms hydrides that can take on both conventional and bridging structures, as in certain boron compounds. Hydrogen's presence, elemental forms, and compound behaviors define a foundation for chemistry, physics, and emerging energy research, stretching from the birth of the cosmos to laboratory curiosities and future technologies. Across the universe, hydrogen dominates as the most common element, representing about 3/4 of normal matter by mass, and more than 90% by atomic number. Soon after the Big Bang, protons appeared, and as the universe cooled hundreds of thousands of years later, electrons became bound to these protons, creating neutral hydrogen atoms. In the interstellar medium, non-ionized hydrogen referred to as H1 prevails until stars form, when photons from these new stars ionize the hydrogen, creating regions known as H2. As these ionized regions expand, they shape the environment where galaxies form. The 21-centimeter emission line characteristic of neutral hydrogen allows astronomers to map this early matter and study structures that existed billions of years ago. Damped Lyman alpha systems, rich in neutral hydrogen, have a key role in the makeup of matter seen in the early cosmos. Within stars and the massive planets composed largely of gas, hydrogen dominates. In these settings, hydrogen exists mainly as H2 molecules in dense clouds where new stars are born. It serves as the principal fuel for stars, fusing to create heavier elements through different nuclear reactions, such as the proton-proton mechanism in smaller stars and the CNO cycle in stars larger than the Sun. The ionized form H3+ is abundant in space and helps drive chemical changes both between stars and within some planet atmospheres, including Jupiter. Neutral H3, however, is only found in excited, unstable forms. Nevertheless, hydrogen is present in sufficient quantities to be metabolized by some bacteria, and recently, significant underground hydrogen reserves have been identified in different parts of the world. Whether these can be extracted in ways that make economic sense remains uncertain. While hydrogen production today relies mainly on fossil fuels, there are several pathways to obtain it. The most common method is the high-temperature reaction of methane and steam, which results in carbon monoxide and hydrogen. Often this is followed by further reactions with water, converting carbon monoxide to carbon dioxide and additional hydrogen. This process, however, results in considerable greenhouse gas emissions, both from the main reaction and from methane released during natural gas production. Partial oxidation of hydrocarbons provides another route, as does the gasification of coal, though these approaches are less central to current hydrogen output. Byproducts from chemical processes such as olefin production can yield substantial hydrogen as well. Electrolysis, which uses electricity to split water into hydrogen and oxygen, is conceptually direct and enables the production of green hydrogen when powered by renewable sources. However, it remains more costly than methods that use fossil fuels, even with carbon capture. Advances in electrolyzer technology, though, could lower these costs. Another approach, methane pyrolysis, produces hydrogen and solid carbon, which might offer a lower emission alternative if challenges with catalyst fouling are resolved. Biological production methods include hydrogen released by certain enzymes in microbes and algae, both through specialized metabolic processes and through genetic modification to boost hydrogen release. This route is being explored in both free-living organisms and engineered algae grown in controlled environments. On Earth, geological activity, especially the alteration of minerals like phyolite and olivine during the process of serpentinization, produces hydrogen, along with other minerals and water. This reaction can also drive hydrogen release during the corrosion of buried iron in low-oxygen environments. Smaller quantities of hydrogen are prepared in laboratories, mainly by the action of acids on metals like zinc and iron, or via the electrolysis of water. In high alkaline solutions, even passivated metals such as aluminum, when alloyed with gallium, can liberate hydrogen under the right conditions. Storing hydrogen poses persistent challenges. It dissolves poorly in solvents, requires energy for compression, and is difficult to liquefy due to its low critical temperature. Some metals can reversibly absorb hydrogen, offering one approach, but their hydrogen capacity remains low. Certain compounds, such as ammonia boron, contain much larger percentages of hydrogen, yet often cannot be reused after hydrogen extraction. Hydrocarbons like tetrahydroquinoline may serve as candidate carriers because they can reversibly take up and give off hydrogen under appropriate conditions. Large volumes of hydrogen are consumed in refining fossil fuels, mainly for removing impurities like sulfur and for transforming heavier oils. The greatest hydrogen sink is the Haber process, which synthesizes ammonia used widely in agriculture. Hydrogen's roles also include producing margarine by hydrogenating fats, manufacturing methanol from carbon dioxide, and serving as a reducing agent for extracting metals from ores. Hydrogen is widely discussed as an energy carrier. Used in fuel cells, it generates electricity and produces only water as exhaust at the point of use. When burned, it yields little direct pollution, though nitrogen oxide emissions can result from the high-temperature combustion process. Green hydrogen made without emitting greenhouse gases may help reduce emissions in sectors where direct electrification is difficult, such as steel and chemical production. In steel manufacturing, hydrogen can replace coal both as a heat source and as a reducing agent, leaving water rather than carbon dioxide as a byproduct. In transportation, hydrogen's role may grow for applications like shipping, aviation, and certain heavy vehicles, especially when converted into derived fuels or used in fuel cells. Its adoption in passenger vehicles, however, lags far behind battery technologies and may remain restricted. For space applications, hydrogen is combined with oxygen to fuel rockets, notable in past programs like the Space Shuttle. NASA has even explored using alternative forms, including atomic hydrogen stored within solid hydrogen, as a propellant. Storing hydrogen produced during periods of surplus renewable electricity opens possibilities for later conversion back to electricity or transformation into synthetic fuels, albeit with challenges in durability, safety, and cost of distribution due to hydrogen's reactivity and storage demands.